Dr. Shamir Shande from University of Oregon, who is a research professor as well as a technologist and also a founder of a tool called Tau, a performance tool, has been there for decades, serving high performance computing industry completely. Um, and certainly, this session is going to be a lot of technical information. Whatever today's need, for AI infrastructure, these kind of tools and platform, definitely required. Without this, these all these kind of, the open AI or whatever you daily use, the cloud or the chat GPT kind of servers, may not be running. So yeah, just want to mention that, to that level actually, like, with that, I'd like to invite Dr. Samir to start his presentation. Samir, go ahead.
Thank you very much for inviting me today, Ganesan. It's a pleasure to present E4S, an HPC AI software ecosystem for science. I hope you can see my screen properly. And the key part I want to come and take this point across is that your software environment should not be your first research project. It has become so difficult to install all the tools in a coherent environment with interoperable software stacks that people spend way too much time in installing their tools and libraries. We need to spend less time configuring our software and more time doing science, more time discovering. And this requires faster onboarding of personnel that will lead to faster discovery. Now, could we have an environment which would be suitable for both HPC and AI tasks? And E4S is one such environment. E4S is a curated SPAC-based distribution of over 125 HPC and AI tools. And in a recent release last month, we had a new release of E4S 2606, which adds much richer agentic AI layer, deeper LLM inference optimization, and more workflow tooling around fine-tuning, serving, and domain-specific AIs. Now, we've got new packages here, including SGLang, MCP, LangChain, LangGraph, agent-to-agent, Flash ATTR, and then we have a coding agent called Pi from pi.dev. We have NemoClaw, OpenClaw. You may have heard of OpenClaw as a agentic AI framework. We have that integrated in E4S, along with other tools like Nemo, BioNemo from NVIDIA, Megatron, Transformers, CuPy, and a range of other tools spanning different disciplines, including RDKit for chemistry. And we have updated Rocky Linux 9.8 images. We also have an Ubuntu 24.04, so you can have both Rocky Linux or Ubuntu. It features SPAC, package manager, and there are many HPC applications that are pre-built. These are applications you may be familiar with, such as CP2K or Quantum Espresso. And we have upgraded CUDA, and we have a multi-user, multi-node environment, an image called Paratools Pro for E4S with both Ubuntu and Rocky flavors available on 5 different cloud platforms. And if you have some time, I would like to show you a demo, and you can try this yourself in the hands-on session today. So E4S is an ecosystem for science, and it's a community effort to provide open source software packages in a distribution that makes it easy to onboard people. And it supports both bare metal installation of HPC and AI packages, as well as containerized distribution, as well as cloud images. So you can use 5 different cloud providers, and we have support for different ISAs, including Intel, including x86-64, PPC64LE, and AR64 or ARM, with GPUs from NVIDIA, AMD, and Intel. We also have some other tools that I'll describe, which allow you to simplify the use of E4S. And here is the web page called e4s.io. You can just go and download the containers directly from here. But you also have a chat bot with OpenAI, and it has been RAG trained with packages from E4S. So you can directly jump in and ask questions like what profiling tools in E4S help with performance, for instance. And it will tell you about Tau, a tool that I've helped develop. And it includes Tau Exec, a tool that you use for launching your applications, or Tau Python for Python-based workflows. Here is the E4S web page for looking at the documentation and facts. And you can just get the E4S containers directly from the container download page, where we have support for GPUs. Instead of having a single container which can get really large, we have partitioned it into Docker Singularity containers for x86, PPC64LE, and AArch64 for different GPUs. So there are separate downloads for NVIDIA GPU, AMD, Intel, and these feature runtimes like CUDA 13.2, ROCm 723, and OneAPI 2026. We also have support for languages like C++, Fortran, Python, Rust, Julia, Chapel, with different OSs and different GPU architectures. So if you have, for example, an H100 GPU, you would download a CUDA 90. If you have an A100 NVIDIA GPU, you would download CUDA 80. And if you have a Blackwell system, then CUDA 120. And you can even do Docker pull directly on these images. And we have the SPAC package manager. You can say SPAC find, and it will list the packages that are there, that are installed. And here is, for example, a Rocky Linux 9.8 Singularity image, which you can launch with Singularity container runtime. And here is an example of CUDA Rocky Linux 9.8 with just CUDA packages. So you can see which ones have support for CUDA, like MFEM or Trinos or Tau. Now, this is interesting. I'm sure you're using Python extensively. Have a look at these packages. These are some of the AI frameworks that are already integrated and interoperate. You do not have to install any of these tools. They come in the container. So if you download a container, you can just simply launch it, and you will have access to Python, which supports the GPU for tasks like PyTorch. And you'll be able to very easily get up and running. And what is interesting is that all of these tools, whether they are Python-based or SPAC-based, they are extensible. So you can use tools like UV or pip to install new tools that are not there in the distribution. And then you can have a union of tools that are in the read-only file system as well as in your home directory. Here is a Singularity image for Intel with Intel compilers, Intel MPI, and it's built with the latest version of their compilers. And you can see over 100 different tools installed. This is for AMD GPUs with ROCm support. And you have support for AArch64. This can be used right on your Mac laptops. You can use it on M-series laptops, or you can use it on NVIDIA Grace or Grace Hopper kind of systems, where you can, or Grace Blackwell. These are Singularity images that support with the AArch64 architecture. And all of these packages are pre-installed. We even have AArch64 Ubuntu Singularity image with CUDA support and Rocky Linux 9.7 support. You can see these packages. And finally, we also support IBM Power architecture. So if you have a Power 9 or a Power 10 system, you can easily deploy these images. And you'd be surprised at how many people are still using this architecture, IBM PPC64LE. And we have support for CUDA in this architecture. And so if you had like a V100 card, you could use it with that. And this is the Ubuntu Singularity image with CUDA. Now we have a tool called E4S CL. It's used to launch containers. So until now, we have been typically distributing our message passing interface applications in a source tarball, where people download the tarball, they compile their application, and then run it. Instead of that, you can use a container. You can create a binary with MPI which resides inside the container with all the packages, numerical libraries, including PETC, Trilinos, compiled with the MPI inside the container, and then launch it on a different system with bare metal MPI substitution. So you can just swap one MPI with another using E4S CL. And it works like this. You can just say and initialize the E4S CL. After loading the module, you can say the backend is Docker or Singularity. Here is the image. And what you need to do to bootstrap a container image. So it might be something like source the setup environment for SPAC and then load the Trilinos with the CUDA variant. And you could say, please use CUDA architecture of 90 for, say, an H100. And then once this is done, it initializes it with the MPI in your path. So you could just say E4SCL srun or MPI run, and then it will substitute the MPI in the image in the application a.out with the system MPI in your path. So you'll get very good performance in the cross-box multi-node executions with this MPI replacement. We also provide a range of containers. We have base images, we have images with the GPU runtimes and full-featured images. And we show you how we have built all of this infrastructure. So you could use a tool called E4S a la carte or E4S ALC as we call it, and say, please start with this base image of the container, add these tools and packages, and create a new container image for me. And then you can just simply use that. This avoids the struggle many people have in writing Singularity images, descriptions in singularity.def files or writing Docker files to create Docker containers. You can just start with E4S ALC and just say, start with this container, add these tarballs, add these system packages or SPAC packages, and then create a new container image. This is how a tool called E4S chainspack.sh works. You can tell it to install a second SPAC in your home directory, and then you can simply replace the SPAC so that you see a union of all the packages that are there in the SPAC in the read-only file system with the packages that you have just installed in your home directory. So you can just do a SPAC install for, say, Valgrind if it's not there, and then you can just see what the Valgrind looks like. So with this tool, you can install new packages while leveraging all the packages that are pre-installed in the container image. Now, I mentioned about using this on your laptops, your desktops, and doing even bare metal installation of E4S using SPAC. But what about cloud platforms? To target commercial cloud platforms, we have support for ParaTools Pro for E4S. Now, when you go to the cloud platforms, there are some key considerations. The first important consideration is, which internode communication library implementation should I use for the message passing interface? There are many, including Intel MPI, MVAPage, OpenMPI. There are different job scheduling packages like Moab, Torque, Slurm. There are different network adapters, including the Elastic Fabric Adapter on AWS, InfiniBand, Mellanox ConnectX 5, IPUs, VNix on different cloud providers as diverse as AWS, Azure, Oracle, Google Cloud, or IBM Cloud. There's also a key consideration of using efficient intra-node communication using XPMEM, cross-memory attach, so that you can have very responsive communication between MPI tasks on the same node, not just intra-node, and support for GPU memory so that you can do transfers between GPU memory to GPU memory across different nodes using MVAPitch. So we are building a whole stack of E4S optimized with MVAPitch Plus for different cloud platforms. And we use Adaptive Computing's HYDE to launch the E4S jobs on multiple cloud platforms. This is how it looks. You can have the same interface to target on-prem systems as well as cloud systems, and you can deploy the common E4S image, which is available in the commercial cloud platforms marketplace. So you can go to all of these marketplace image sites. You can start with paratoolspro.com, and then you can see all the different cloud providers that are present. And this is typically ideally suited for, training workshops and learning environments for higher education, for even grades K through 12, and using, cloud images is the next frontier. So here is the typical view of Paratools Pro for E4S on AWS Marketplace, and you can see the SDKs that it includes, including support for hardware like Trainium and Inferentia nodes. And we have support for Slurm and Torque, and it also includes support for the Elastic Fabric Adapter. We have support for Azure or Google Cloud or Oracle Cloud or the IBM Cloud. All of them have the Paratools Pro for E4S. You can launch this. For the hands-on, those who would like to try this, we can just go to paratools.adaptivecomputing.com. You can go to my slide number 40, and just enter the code in the workshops tab of 4070034. Looks like this. Just go to this web page, enter this code, put your email address. It will send you a two-factor authentication code. When you receive it, you can just simply click on the deployed cluster and then launch a remote desktop. It will show you a remote desktop. You may have to enable pop-up windows, and then you have a remote desktop. And this is Ubuntu or Rocky Linux, and you can click on a terminal window. You can even upload, download files. You have audio going both ways, so you can launch a web browser and view videos. You can launch 3D visualization tools like ParaView, and the whole remote desktop is GPU accelerated. And you can see here is a Marimo reactive notebook. There is a visit visualization tool. We even have VS Codium, or the Visual Studio integrated development tool, with all the packages such as NVIDIA BioNeMo and a range of other packages, where you can see that the GLX info is using the NVIDIA GPU, and you have good frame rates. So in conclusion, I would like to just say that please use E4S containers to save you time as you look at HPC and AI tasks. There's a very good chance that the packages that you're looking for are already pre-installed, and those that are not, you can add to it and you can install using the tools provided. We also have support for E4S ALC, which allows you to start with a E4S container, add new packages to it, and create your custom software stack, which will save you a lot of time rather than starting from a scratch. And you can substitute the MPI embedded in your container image or in your applications that use containers with the system MPI using a tool called E4SCL, and you can also run on cloud platforms. I'd like to thank the US Department of Energy, Office of Science, and the various projects that have supported this development. And I'll show you a live demo of this environment. So here is an environment. This is the Heidi AI. This is what you get when you are launching a particular image over here. And I'm just going to launch this terminal window. Now here, I can see that there is a L4 GPU. How do I get to this image? Well, you can simply go to this slide number 40, and it shows you a particular code. You go to paratools.adaptivecomputing.com. You click on this workshops tab, enter this code 70034 and your email, and maybe a Gmail address where you can see it on your phone, and it will show you the two-factor authentication code that you enter. Then you click on this deployed cluster, and then you can click on the remote desktop, and it will launch this image where you can open up a terminal window. Now, in this case, I have an L4 GPU and I have 2 compute nodes. Okay, so here is, for instance, the cluster, and I can see that there are 2 compute nodes with 1 GPU on the login node, 1 GPU on each of the compute nodes running on IBM Cloud in this instance. And then I can see the GPU, general metrics, GPU metrics. This is the Heidi software from Adaptive Computing. And you can see the performance, even do IO performance and testing. And here is the remote desktop. And I have a web browser, I have a full desktop, and this is across the country. But still, if I say GLX info, I can see that it's using the NVIDIA GPU. It also has a Python with many of the tools that I described. And if I run GLX gears, let's see what frame rates we get going across the country. You may be used to like 30, 40 frames per second, but I'm seeing over 4,800 frames per second in this frame rate. You can try this. Here is a set of examples. Let me just go to examples, MPI proc name, and compile a simple MPI code that looks like this. This is the message passing library. I'm doing initialization, finalize, rank, size, processor name, and just printing a hello world message from nranks. And if I do a MPI proc name.sbatch, I'm saying let's take 2 nodes, put 4 tasks with 2 tasks per node, and then run this MPI application, which I can do like this, MPI proc name.sbatch, and then look at the queue for the user, and you can see this is job is pending. If I look at it again, it's finished, and I should have a slurm3.out because this is job ID 3. And there it is, ranks going from 0 to 3 out of 4, and 0, 0 node, 0, 1 node, 0, 0, 0, 1. So it's wired correctly with Slurm with packages like srun. So you have MPI, you have Slurm, and support for GPUs. Let me just go to let me use a simple example with, say, the PETSI solver. And I'm compiling. I have many libraries here. You can see HDF5, Parmetis, Metis, CUDA, and cuSolver. And if I look at SPAC find, I see over 100 different packages that are pre-installed in this environment using SPAC, or I can say module avail. And you can see all of these packages like GROMACS, one with OpenMP for the CPU, one with CUDA for the GPU, Quantum Espresso, or other libraries like Tau or Trilinos or PETSI There is Petsy with OpenMP, with CUDA, and you can easily load these packages. We also have tools like UV, Pixie. We even have languages like Julia, which are part of the distribution. So here, I'll just try a simple example. Here is the C example for Petsy. You can see this. And then I have a bench sbatch file. I can just say sbatch bench ksp-sol.sbatch sq, and then monitor the job. This is very much like using a cluster, and this is a slurm 4.out. This is the job ID. And you can see it ran this job. If I want to measure the performance of this application, I can simply use a tool called Tau, and I say Tau exec, and then run this, and maybe even say sbatch tau.sbatch. And once this is done, I'll see the slurm 5.out, and you can see the tool is registered, and I can launch Paraprof to view the performance of the application. So here I can see exactly how much time was spent in CUDA memory async. I can look at the time spent in different kernels running on the GPU. And here is a cuSparse kernel running on the GPU. I can look at how it performs across different codes, different MPI ranks on thread 5. I can even see a 3D visualization of this, showing me the MPI ranks and threads, including the GPUs. And here's a bar plot. I can use the function and thread sliders like this. And where they intersect, I can see the time and the color value. Here is the color scale. And you can explore the performance of your application in 3D in this image and get the detailed information about execution along the GPUs. If I want to generate trace files, all I have to do is add a tau trace environment variable. So I can say export tau trace equals 1, export tau trace format equals perfetto, and then just run sbatch with tau.sbatch. And I will have a tau.perfetto.gz file that's created. And I can, of course, check the slurm 6.out. In this case, this is the job 6. And there it is, the execution of the code. And I can just launch Firefox and go to perfetto.dev. Perfetto is a tool developed by Google. And because I have a remote desktop, I can simply visualize this very easily within Perfetto by here. I'll just say go to the trace viewer, open the user interface, and then I'll connect to the user interface and load my trace file like this open trace. And here is the perfetto.gz file, and click open. And now I'm loading the trace file and seeing what the CPU is doing, what the GPU is doing across the two nodes. And I can open this up and see a full flame graph, which shows me this is the time spent in MPI collective sync. That is the time wasted in a barrier within a collective operation. I'm looking at two different threads here. You can see the matrix operations. Here is a MPI all gather. I can zoom in, and you can see over here that it's waiting in this MPI all gather And while it's waiting, the other threads are not there. And this is the collective sink, the time wasted in the MPI in a barrier. Now let me just zoom in all the way to what and see what the GPU is doing. This is the CUDA thread. And you can see the CUDA memory copy, vector scatter begin, matrix multiply. And this is what the CUDA is doing on different ranks. And you can see here is one, this is the other, CUDA cuSparse kernels. So you can see exactly what's happening inside the CPU, in the GPU, and who's doing what when along a timeline display. So you can see the execution of kernels on the GPUs, whether it's a Python application or MPI application, and very easily measure the performance of your code and see exactly what your application is doing over the execution like this. Instead of Python, you can use Tau Python and launch this. And there are many tools like Python, and you can say import, import A2A. You can import, say, Torch or PyTorch, and then you can see what GPUs are supported within that. So here is the torch.cuda.get arch list. And you can see that it supports all the way from V100 to A100, going to H100 to Blackwell GPUs, and different tools like I showed you. And of course, ADK is installed externally. We have NemoClaw or OpenClaw as well over here. And other tools like NPM. So if you were trying to install something like Claude, and of course, we don't have Claude in this image, you could simply say npm install -g Anthropic AI Claude code. And with this, it will run this, and you will be able to run Claude after that. And then you can provide with Claude your credentials with Anthropic and then just use this. So it simplifies the installation, whatever you may be trying to install. Like if you wanted to install with GitHub, it will simply install the Copilot here. And each user has full control over which packages are installed. We already shipped some packages such as Gemini from Google, but you can then launch Copilot and just run that over here. Or if you were using OpenClaw, which is very popular for agentic AI development, you can just run that directly with OpenClaw on board, and then you can do the quick start and so on. Or NemoClaw as well. What other packages do you typically use? Gemini with the API and the interface, and you can launch a web browser to connect with Google very easily, like this. And you can authenticate and launch Gemini. Or if you are using Codium, each user can customize their own environment. And here, I click on extensions, and I can simply install the extensions I care about, say Python in this case. I can say trust the publishers, and then open a project folder like examples, maybe PyTorch GPU. And here I can open up this and then run the environment. So with this Heidi, you can then launch the image that you're
So,
interested in, and then uh, you know get the full AI environment in your cloud. So I'll pause here and see if there are any questions.
yeah, team Rahul, do you have any question? Rahul, Krish?
No, sir, I'm clear till now, sir.
Okay. So you, Rahul, you can try these tools, right?
Yes, I can
Okay.
give them a try.
So go ahead, download the containers if you would like, and use it on the cloud platforms, or use it on your on-prem systems, or connect to uh, our image on various cloud platforms. And if you would like to try this for the hands-on, here are the instructions. And you can just get the Rocky Linux 9.8 image running on this. I hope this was useful to you and you are able to try this out on your own. And I would love to hear what are your use cases, what kind of packages you're using. Are you using agentic AI tools? Are you using, OpenClaw or
Rahul, you can respond to that, Rahul.
Yeah, so like I'll be experimenting with AI workloads. Like I'll be using either platforms or any other LangChain frameworks or language frameworks. Like when I
you are
want to work
using
with
LangChain, LangGraph?
yeah, so like if I want to build something like of LLMs, so I want to build any
Yes.
applications, I'll be using them. Like when I need to like create any proof of concepts for agentic AI, so I'll be using any agent architecture which is available. So it depends on the like on the problem statement I'm working on. So even I'm like experimenting with ML flow also. So like I can also use them using Flores.
So do some of these packages look familiar to you? Are you
Yeah,
using
like,
some of these tools?
yeah. I'm using them. Like I'll be using torch transformers, and like LangGraph, LangChain, MCP A2A, MLflow, OpenAI. So like most of the like packages, I'm just using them either in my applications or anything related to experimentations or prototyping.
So this will help you with, getting a container will help you in reducing the time it takes to deploy all of those packages. You know how hard it is sometimes when you try to install Python packages and it has
Yeah.
incompatibilities with other Python packages that are
Yes.
not working properly. And then you
Yeah.
waste hours and days trying to get an environment where the right versions of these tools interoperate and work together, right?
Yes.
So having a container to just boot up and get productive right away can cut down a lot of that effort of installing software. Otherwise, you could be wasting a lot of time in just getting an environment that works properly for you.
Yeah. I think that's where E4S will be looking out. So yeah, I will just try to implement in upcoming experiments or prototypes. What I'm going to do, like
Great.
even with yeah, I can also use with MPI to demonstrate exclusive stuff. So I need also
With
like
MPI.
yeah, so I need to also try them out. And also I wanna also do a try to tau to like evaluate the performance. Yeah. So I need to
Evaluate the
also
performance using Tau.
yeah,
Absolutely. And Tau is, as you know, part of the E4S environment. And
yes.
you can see that Tau 235.2 is now integrated in our images. And we support both Rocky Linux and Ubuntu systems. So that should help.
Arshad, you have any questions, Arshad, for Samir?
Well, I hope you found this informative and it opens up new opportunities for you to reduce the headache of software installations using containers and cloud images that are ready to boot and already have many of the tools, if not all, that you typically use in your workflow. So if you find this list of tools interesting, I would highly recommend that you download our containers, get started, or if you need access to cloud platforms, maybe you can reach out to me through Ganesan and I can even boot up these cloud images on demand for you.